Alright, so here we have a problem. A 960 kilonewton load P is applied to the granite block shown below, this one right here. Determine the resulting maximum value of A, the normal stress, and B, the shearing stress, and we have to specify the orientation of the plane on which each of these maximum values occurs. So we have to find practically three things here. So let's take a look at this problem right here, particularly this figure. One thing we can find immediately is that this load P is actually it's actually applied parallel to the axis or to the length of this granite block, and what that means is that this is actually an axial loading problem, because axial loadings happen when your force is applied parallel to the length of the surface. So it's pretty simple at that point actually. For normal stress under axial loading, you actually have a formula which is sigma is equal to pressure divided by the area. Now normally we would just plug that in there and would be done, but the problem here is that it's actually asking for maximum value of our normal stress. And so what that means is that we're actually applying our load P here at a certain angle to achieve maximum normal stress. And so our formula actually changes a little bit into this one right here. Sigma angle is equal to P, or force, divided by our area naught times cosine squared theta, in which theta is our angle at which we would be applying our load. Now, where this formula comes from, would actually need to prove this using geometry, and for the interest of time I would not be doing that here, but you can flip to your textbook. It's most likely there, but for the most part you're just gonna have to trust me on this. This is the right formula. So moving on, we're gonna have to find that theta in which we'd achieve maximum. Again, this is already proven. I'm just gonna throw it out there that the maximum is actually 0 degrees. Now doing the logistic math here, cosine squared 0 is actually 1, so that's your final formula for your maximum normal stress. This is your general formula, is P over A naught. So it's actually quite similar to our original formula, but you know, this one is actually different if you consider the process. So again, we just plug that in there, 960 times 10 to the power of 3 newtons divided by our area, which is, yeah, that's 150 millimeters by 150 millimeters, so that's essentially a square. Convert that into SI units, that is 0.15 meters squared. Plug that into your calculator and you get approximately 42.67 megapascals. And for our orientation, that would be 0 degrees, since, well, that's the angle that we applied it. And so that's A. We're practically done. Let's move on to B. B finds, we're trying to find the maximum shearing stress, and like A, actually this is pretty similar. The process is actually pretty similar. We have a general formula for shearing stress under axial loading, which is P over A. Get that out of the way. But since we're doing it on an angle, it's gonna change to P over A sine theta cos theta. Again, you're just gonna trust me. You're just gonna have to trust me on this. Now, you can try to prove this on your own, but eventually this was already proven, and that it's the angle in which you're gonna apply it to achieve maximum shearing stress is actually 45 degrees. And if you actually think about it, it intuitively makes sense, because by definition, shearing stress is the stress in which things start slipping from each other. And 45 degrees is that sweet spot, because anything too shallow would be anything lower would be too shallow, and anything too higher would be too deep. And so doing the logistics, that would be square root of 2 over 2 multiplied by square root of 2 over 2. You get a 1/2, so you get a final formula of P over 2A naught. Again, just plugging it all in there, 960 times 10 to the power of 3 newtons divided by 2 times 0.15 meters squared. Plug that into the calculator, and you get an answer of approximately 21.33 megapascals. And again, since we used 45 degrees, our orientation of the plane would be 45 degrees as well. So there you have it.